Welcome to section 5.3, the definite integral as area. So we've already mentioned that the definite integral calculates the area under a curve. Today we're going to get a little bit more specific. Alright, so we're going to put it into words here. So when a function f of x is positive, and we have 2 points a less than b, then the area under the graph of the function f between the 2 points a and b, well, that's given by the integral from a to b of the function f of x. Okay? So graphically, if we have a function that looks like this is f of x, and we are positive because we are above the x-axis, right? And we have points a and b where a is less than b. So if we take the integral, we would get this shaded area, right? So now we're going to talk about the concept of signed area. This is a little bit of a tricky concept sometimes to start out with. Alright, but take a function that looks like this. Based on what we know, alright, the area between a and b here, and the area between c and d is positive, right? We just wrote that down. Okay, but what about between b and c and d and e? Alright, this is where we introduce the idea of, I'm going to put this in quotes, okay, negative area. Alright, between b and c and d and e over here. And I put it in quotes because area can't be negative, right? You can't have a negative area, that just doesn't make sense. However, we are going to count this area negatively when we're trying to find the total area encompassed by this function. Alright, so for an example, if we wanted the total area of, I'll call this g of x, is the area from a to b minus the area from b to c plus the area from c to d, and then minus the area from d to e. Okay? So we're technically subtracting this area. The area itself isn't negative, but I think it helps to think of it that way. Okay? So if we actually wanted to know the total area enclosed, so this is the total area where we add and subtract, okay? But if we wanted to know like the absolute value of the area, so if we wanted, let's say, to tally all of the area enclosed, basically no matter if it was positive or negative. Like, we just wanted to know in total how much was there positive and negative combined, like all of it total. Alright, we just take the absolute value of all of the areas. Okay? So in general, when you're asked to find the total area, then you'll be adding and subtracting respectively. But if it specifically says find all of the area encompassed by a function, then you would take the absolute values. Okay? So let's go ahead and jump into our first example. So we want to use the following graph to find the desired integral values. And our first one, part A, is the integral from 0 to 2 of our function. So 0 is not labeled, but it's this point over here. Okay. And so we are looking at this shaded region. So we are looking from 0 to 2. So we are above the x-axis, so we know we are going to be positive. And all of the area values are labeled for us here. So we're not doing any calculations really. We're just identifying. Okay? So then our area is 2.5, whatever area units we're using. Okay? Part B asks us to look at the integral from 2 to 3. So this shaded region here. Well, we are below the x-axis. So this is where it's going to be counted as negative. Alright, so we have negative 0.75. Part C asks us what's the total area from 0 all the way to 3. So we need to count the area from 0 to 2, which we just identified in part A, plus the area from 2 to 3, which we just found in part B. So this is going to be 2.5 minus our 0.75. And we get 1.75. Okay. And finally, for part D, we are looking at the region between 3 and 5. So let's scroll back up. 3 starts here, and 5 is up here. So we need to take into account both of these regions. And this is a poorly drawn 2, okay? That's my drawing for you. That's a 2. So we have a positive 2 and a negative 2. So we end up with 2 minus 2. So we get the net area, okay? Our net area is 0. So when calculating net area, sometimes area will cancel out. So it's okay to end up with a 0 area, alright? Because sometimes it will cancel out. And I know at least one of you plays cornhole, so I'm going to attempt to give you an analogy here. So think about if your opponent gets a bag in the hole, okay? So that's a positive 3 points, right? However, if you get one of your bags on the board, that's going to cancel out 1 point from his 3. Alright, so if you can think about your opponent's points being above the x-axis and then your points being below the x-axis, that is how we're going to calculate the net area. So only one team ends up getting points after one round of cornhole. Alright, so you'll either end up with a total being positive, a total being negative, or sometimes neither team will get any points because you'll cancel each other out entirely. Alright, so now we're going to get to area between two curves. Alright, so let's write this out first. So if we have a function f and another function g, okay, so if f and g are continuous functions, there we go, and this is the important part, let's say g is less than f, alright, for some values a to b, alright, so the area between the functions f and g from a to b is given by the integral from a up to b of the function f of x minus the function g of x. And I'm going to go ahead and put these in parentheses with respect to x. Okay, and I put this subtraction here in parentheses because we want it to be super clear that we're taking the integral of both f and g and not just one part of that. Okay? So let's look at what this means on a graph. Alright, so let's look at, let's say this is our function f of x. Okay? And let's say we have a to b over here. So our area for f of x would be given here. Okay? And then let's look at g of x. So our g of x, let's say it's a parabola, so it looks something like this. Let's pretend it crosses at the same point there. Okay? So the area under that parabola is down here. And we want to know, well, what's the area between the two? Okay, so what is this area in between these two functions? Well, we need to first identify the quote-unquote top function and bottom function. So this is our top function. Okay, and g of x is going to be our bottom function. And I didn't label g of x on the graph. G of x, there we go. Okay, and we know this because we have g of x is less than f of x. Okay, we can also look at our graph and just kind of intuitively think, well, f of x seems to be on top of g of x between these 2 points. Okay, so that's how we can choose our top function. And so we just need the total area that f would give us minus the total area that g would give us. Okay? And that's how we're going to find the area between the 2 functions. Area between, oops, it needs another e, f and g. Alright? And that leads us to our second example. We want to find the area between our 2 curves. So we have y is equal to x squared and y is equal to 8 minus x squared. So the first thing we need to do is go ahead and graph them. We want to see what we are dealing with here. Alright? So I'm just going to do a rough sketch here. X squared, well, we know that's an upwards facing parabola, right? So here we go. And it's centered at 0, so this is our y is equal to x squared. And then y is equal to 8 minus x squared. Well, that's going to be an upside down parabola raised up to 8 up here. Okay, so we're going to have an upside down parabola. There we go. So the area that we're interested in is between these 2 curves. Now notice we were not given the a to b. We were not given the bounds or our limits for our integral. Okay, so we actually need to find them. Based on our graph, we would like to know where our 2 graphs intersect. And these will be our points A and B. Okay? So we need to find limits of integration. So we're going to do that by setting our equations equal to each other. That's how we can find, well, where do they equal each other? So we set x squared equal to 8 minus x squared. Go ahead and add x squared to both sides, so we get 2x squared is equal to 8. Divide by 2, x squared is equal to 4. And take the square root. And when we take the square root, we need both the positive and negative version, right? So we get x is positive and negative 2, which makes sense since we were looking for two different points, right? So this tells us a is negative 2 and b is positive 2. So these are our limits of integration. Next, we need to identify the top function and bottom function. Top and bottom functions. Well, between a and b, let's see, we had this one is y is equal to x squared. And that looks like it's on the bottom to me. So y is equal to x squared is the bottom function. So that means y is equal to 8 minus x squared must be our top function. So now we have all of the pieces, so we need to go ahead and calculate this. So we get the area, so we need the integral, we need our a and b, which is negative 2 up to positive 2, and we need our top function minus our bottom function. So our top function was 8 minus x squared, so parentheses 8 minus x squared. I'm going to go ahead and put these in an extra set of parentheses just to be super clear what we're doing here. Minus our bottom function. So minus x squared. And close parentheses. Don't forget your dx for proper notation. Okay, so now we're going to go ahead and simplify inside of here first. We can drop a few sets of parentheses. So we get integral from negative 2 up to 2 of 8, and then we get negative x squared minus x squared. So we get minus 2x squared dx. And if you go ahead and plug this into your calculator like we learned in the last section, you'll get that the answer is 21.33. Alright, so that is how you calculate the area between two curves. So that's actually it for today. If you have any questions, please send me an email. Don't forget to take the comprehension quiz, and I will see you in the next lecture.